Good morning all. We are discussing about the Biot law. Now let us do a problem from the Biot law. Find the magnetic field a distance s from a long straight wire carrying a steady current I. Now according to Biot law, the magnetic field at a point due to an element of a conductor carrying current is given by dB, that is mu 0 by 4 pi ideal sin theta divided by r square, where I is the strength of the current, dl is the length of the element, and theta is the angle between the element in the direction of the current and the line joining the element to the point P. Now consider the figure A. The distance between the element dl and the point P is given by r, and the current passing through the element is I. Now to solve this problem, we need to evaluate dl. How do you find out dl? Just find out what is L and take the differential. We have from the figure A, L equal to S tan phi. Therefore, dl is given by x sec square phi d phi, or this is equal to S by cos square phi d phi. Also, we need to evaluate what is meant by sin theta. From the figure A, we can see that theta is nothing but 180 minus alpha. 180 minus alpha. Also from the triangle, as you have seen in the figure A, alpha plus 90 plus phi is equal to 180. Therefore, 180 minus alpha is equal to 90 plus phi. Therefore, sin theta is equal to sin 90 plus phi. We know that sin 90 plus phi is cos phi. Therefore, sin theta is nothing but cos phi. Also, to determine dB, we need to evaluate what is the expression for 1 by r square. Again, look into the triangle. We have s by r equal to cos phi. Therefore, 1 by r square, that is equal to cos square phi by s square. Now we have the value for dl, sin theta, and 1 by r square. Now substitute the value of dl, sin theta, and 1 by r square in the equation. dB is equal to mu 0 by 4 pi ideal sin theta by r square. You will get dB, that is equal to mu 0 I by 4 pi s by cos square phi d phi, then cos phi into cos square phi by s square. Here, instead of dl, you have s by cos square phi d phi. Instead of sin theta, you have cos phi. And instead of 1 by r square, you have cos square phi by s square. Hence, dB becomes mu 0 I by 4 pi s cos phi d phi. This expression dB, this is equal to mu 0 I by 4 pi s cos phi d phi. It is a magnetic field at a point P, which is at a distance s from the current carrying wire. Mu 0 I by 4 pi s cos phi d phi is the field due to an element dl carrying current I. Now let us evaluate what is the field due to the entire segment of the wire. What is the field due to the entire segment of the wire? For that, we have to integrate dB. The magnetic field of any straight segment of wire in terms of the initial and final angles phi1 and phi2 is obtained by integrating dB with a limit of integration from phi1 to phi2. To find the magnetic field due to the entire segment of the wire, consider the segment of the wire in terms of initial and final angles phi1 and phi2. See figure B. Thus the field B due to the segment of the wire is given by B is equal to integral phi1 to phi2 mu 0 I by 4 pi s cos phi d phi. Here mu 0 I by 4 pi s is a constant, so you can take it outside the integral. Therefore, B is equal to mu 0 I by 4 pi s integral phi1 to phi2 cos phi d phi. This is equal to mu 0 I by 4 pi s sin phi2 minus sin phi1. This is the magnetic field of any straight segment of wire in terms of initial and final angles, which carries a constant current I. Now, you consider the special case where the length of the wire is infinite, that is, an infinite wire carrying a steady current I. Now, what is the magnetic field due to such an infinite wire carrying a steady current I? What happens to phi1 and phi2 when the length of the wire becomes infinite? If you see the figure B, you can conclude that if the length of the wire is infinite, then phi2 becomes pi by 2 and phi1 becomes minus pi by 2. Hence, the magnetic field due to an infinite wire is given by B is equal to mu 0 I by 4 pi s sin pi by 2 minus sin minus pi by 2. And if you solve this, you will see B is equal to mu 0 I by 2 pi s, that is the magnetic field due to an infinite wire carrying a steady current I.